Philosophy. Sharing and debating circle. The concept of time in modern physics. An exploration from Newton to Einstein and beyond by C. Yalil Arasu. What is time? Time is ubiquitous, a concept so existing everywhere and natural for us, human beings, that we rarely wonder about its nature. For science, there is a clear need of understanding more and more about the fundamental structure of the world around us, so that an understanding about the concept of time surely is a noble target for physics. Time can be defined as an ongoing and continuous sequence of events that occur in succession from past through the present and to the future. Time is used to quantify, measure, or compare the duration of events or the intervals between them, and even sequence events. Simply the measurement between two incidents. Time is divided into three distinct regions: the past, the present, and the future. Using that representational model, the past is generally seen as being immutably fixed, and the future as at least partly undefined. Could you please elaborate further about time? According to its most famous proponent, Sir Isaac Newton, for example, absolute time, which is also sometimes known as Newtonian time, exists independently of any perceiver, progresses at a consistent pace throughout the universe, is measurable but imperceptible, and can only be truly understood mathematically. For Newton, absolute time and space were independent and separate aspects of objective reality, and not dependent on physical events or on each other. Time, in this conception, was external to the universe, and so must be measured independently of the universe. It would continue even if the universe were completely empty of all matter and objects, and essentially represented a kind of container or stage setting within which physical phenomena occur in a completely deterministic way. In Newton's own words, absolute, true, and mathematical time of itself and from its own nature flows equably without relation to anything external. It should be pointed out, though, that the Newtonian version is still a very good approximation of what time is and how it behaves in the world we live in and experience. As we will see, relativistic time only differs from absolute time to any noticeable degree when traveling at speeds approaching the speed of light or in conditions of extremely high gravity. At everyday speeds, everyday common sense, non-relativistic physics applies. What is Einstein's theory of time? The great physical theories of the 20th century have been quantum theory, special relativity, and general relativity. These theories are not independent of each other. General relativity was built on special relativity, and quantum field theory has special relativity and quantum theory as inputs. Let us examine special relativity and general relativity one by one. A child walks along the floor of a moving train. Passengers on the train measure the child's speed and find it to be 1 meter per second. When ground-based observers measure the speed of the same child, they obtain a different value. Observers on an airplane flying overhead obtain still another. Each set of observers obtains a different value when measuring the same physical quantity. Finding the relation between those values is a typical problem in relativity. There is nothing at all startling about these observations. Relativity was not invented by Albert Einstein. Einstein's work did, however, drastically change the way such phenomena are understood. The term relativity, as used today, generally refers to Einstein's theory. The theory of relativity of time is called special relativity. The theory of relativity of space is called general relativity. Special relativity is based on the two postulates. Postulate 1. Principle of relativity. The laws of nature are the same in all inertial frames. Postulate 2. Constancy of the velocity of light. The speed of light in empty space is an absolute constant of nature and is independent of the motion of the emitting body. The new theory of curved spacetime was called general relativity to distinguish it from the original theory without gravity, which was now known as special relativity. It was confirmed in a spectacular fashion in 1919 when a British expedition to West Africa observed a slight bending of light from a star passing near the sun during an eclipse. This was direct evidence that space and time are warped, and it spurred the greatest change in our perception of the universe in which we live since Euclid wrote his Elements of Geometry around 300 BC. Before 1915, space and time were thought of as a fixed arena in which events took place, but which was not affected by what happened in it. This was true even of the special theory of relativity. Bodies moved, forces attracted and repelled, but time and space simply continued, unaffected. It was natural to think that space and time went on forever. The situation, however, is quite different in the general theory of relativity. Space and time are now dynamic quantities. When a body moves or a force acts, it affects the curvature of space and time, and in turn, the structure of space-time affects the way in which bodies move and forces act. Space and time not only affect, but also are affected by everything that happens in the universe. Just as one cannot talk about events in the universe without the notions of space and time, so in general, relativity, it became meaningless to talk about space and time outside the limits of the universe. It was Einstein's genius to realize that the speed of light is absolute, invariable, and cannot be exceeded. And indeed, that the speed of light is actually more fundamental than either time or space. In relativity, time is certainly an integral part of the very fabric of the universe and cannot exist apart from the universe. But if the speed of light is invariable and absolute, Einstein realized both space and time must be flexible and relative to accommodate this. Although much of Einstein's work is often considered difficult or counterintuitive, his theories have proved, both in laboratory experiments and in astronomical observations, to be a remarkably accurate model of reality. Indeed, much more accurate than Newtonian physics, and applicable in a much wider range of circumstances and conditions. According to relativity, the perception of a now, and particularly of a now that moves along in time so that time appears to flow, therefore arises purely as a result of human consciousness and the way our brains are wired, perhaps as an evolutionary tool to help us deal with the world around us, even if it does not actually reflect the reality. As Einstein himself remarked, people like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion. With the general theory of relativity, the concept of space-time was further refined. When Einstein realized that perhaps gravity is not a field or force on top of space-time, but a feature of space-time itself. Thus, the space-time continuum is actually warped and curved by mass and energy, a warping that we think of as gravity, resulting in a dynamically curved space-time. In regions of very large masses, such as stars and black holes, space-time is bent or warped substantially by the extreme gravity of the masses, an idea often illustrated by the image of a rubber sheet distorted by the weight of a bowling ball. In general relativity, gravity is due to the warping of space caused by the presence of a large mass. The Earth moves around the Sun, not because some mysterious invisible force pulls it, but because of the warping space due to the sun's enormous mass. What is time dilation? Time dilation is just one consequence of the theory of relativity and curved spacetime. Einstein's work and his special theory of relativity, we now know that rates of time actually run differently depending on relative motion, so that time effectively passes at different rates for different observers traveling at different speeds, an effect known as time dilation. Thus, two synchronized clocks will not necessarily stay synchronized if they move relative to each other. There is a related effect in the spatial dimensions known as length contraction, whereby moving bodies are actually foreshortened in the direction of their travel. Time dilation, as well as the associated length contraction, is negligible and all but imperceptible at everyday speeds in the world around us, although it can be, and has been, measured with very sensitive instruments. Perhaps the easiest way to think of this difficult concept is that when an object or person moves in space-time, its movement shares some of its spatial movement with movement in time, in the same way as some northward movement is shared with westward movement when we travel northwest. What forces this sharing of dimensions is the invariant nature of the speed of light, which is a fundamental constant of the universe that can never be exceeded. Thus, the slowing of time at relativistic speeds occurs, in a sense, to protect the inviolable cosmic speed limit, the speed of light. According to Einstein, then, time is relative to the observer, and more specifically to the motion of that observer. This is not to say that time is in some way capricious or random in nature. It is still governed by the laws of physics and entirely predictable in its manifestations. It is just not absolute and universal as Newton thought. And things are not quite as simple and straightforward as he had believed. How does relativity theory explain the twin paradox? The dilation of time also gives rise to the so-called twins paradox or clock paradox, whereby a hypothetical astronaut returns from a near light-speed voyage in space to find his stay-at-home twin many years older than him, as traveling at relativistic high speeds has allowed the astronaut to experience only, say, 1 year of time, 1 year 20, while 10 years have elapsed on Earth. Because of the time dilation effect, a clock in the spaceship literally registers a shorter duration for the journey than the clock in mission control on Earth.
The real paradox, though, as Einstein explained it, arises from the fact that, because there is no preferred frame of reference in relativity, we could just as easily consider the traveler in the spaceship as the one remaining at rest, while the Earth shoots off and back at close to the speed of light. In that scenario, Einstein argued, one would expect the astronaut to age much more than the inhabitants of the Earth. In fact, the paradox is explained by Mach's principle. The spaceship is accelerating away at near light speed from the bulk of the universe, whereas the Earth is not. Hence, it is the spaceship and its astronaut that experiences the relativistic time dilation, not the Earth. Quantum theory is arguably the most wide-ranging, highly accurate, and economically rewarding theory of all time. Regarding the first claim, although quantum physics deals primarily with small things such as photons and atoms, it has major implications for big things such as the universe. How do we know the age of the universe time is relative according to Einstein?
The age of an object is, by definition, measured in its proper frame. That is, the frame in which that object has zero velocity. For the universe, we must measure the age separately at each object in the universe. According to our current understanding, the ages at each point all roughly agree, with the answer being about 14 billion years. They only agree roughly because the expansion is not completely uniform, and objects such as the Milky Way galaxy do have some proper motion that departs from the Hubble expansion. Time for us is a specific measurement of Sun's trajectory from a fixed point on Earth. Time cannot be measured from any other planet or any other point in universe the same way as we humans perceive time. Moreover, biological ability of an alien or other creature could be faster or slower to observe the movement of object, and their calculations will be based on their personal observation and not human observation. So far, so good. But here is where everything turns. There are many approaches toward understanding the phenomenon of time. We, as individuals, perceive time as past, present, and future. But in physics, time plays a major role in measurement of motion and forces. Einstein's relativity introduced the concept of slowing of time in motion and gravity, which have been precisely confirmed. The time is relative, which makes the universe age relative as well. Time is a concept that is used to describe and measure rate of change. We even describe a situation in which everything stops changing, freezes as time stopped. Time is your imagination. Time is a human construct. Time and space came into existence only after the Big Bang, and so our laws based on these quantities can only be used after the Big Bang. Many people have asked this question, but no one can determine what really sparked the beginning of the universe. Time is most certainly relative, as the theory of relativity predicted. Time is relative and can change depending on two different factors: velocity and gravity. The higher the gravitational influence you're experiencing, the slower time will be for you. In reference to bodies experiencing lower amounts of gravitational influence, the same has to do with the velocity. The higher you go, the slower things are. What is the concept of quantum time? Quantum reality is a bizarre world of both ands and, whereas macroscopic world is ruled by either or. The most outstanding problem in modern physics is to explain how the both and is converted to either or during the act of observation. We have long known that particles can be in a superposition, both here and there at the same time. We can measure this in the laboratory, but does this also hold true for larger objects? That is the question. Quantum reality is both and means both waves and particles, both here and there, now and then. Thus, the many possibilities carried by quantum superpositions are spread out over space and time. Yet we live at the level of ordinary experience in a either-or position in the macro world. The logic of time in quantum world is unique. In quantum mechanics, therefore, there is a difference between the past and the future. The two are not simply reversible. In the past, there are facts. The future, on the other hand, is open, and all measurements of observables are made at certain instants of time. Thus, time has somewhat different properties and qualities in the quantum world, but it is still recognized as part of reality by quantum physics. According to quantum physics, universe is probabilistic. The evolution of a quantum state can happen in multiple ways. Quantum mechanics is not a thing that exists. It's a way to explain the universe on a micro-subatomic scale. It is a set of laws developed by physicists over the last century to describe how particles behave in certain situations and why our universe is the way it is. What is the conclusion of the story of time? Thus, the inconclusive conclusion. Time presents to us in numerous ways, which possibly creates difficulty in understanding this phenomenon. We are immersed in time, yet we do not fully understand it. We know that time is closely linked to motion as well as forces. Theory of relativity introduced the concept of slowing of time with motion and gravity. This breakthrough could have led to further progress in understanding of time, and possibly the cause of time, however. Almost 100 years have passed without substantial progress. In brief, Isaac Newton founded classical mechanics on the view that time is something that passes uniformly without regard to whatever happens in the world. Albert Einstein proposed that the laws of physics should be based on the principle of relativity. The modern science following Einstein's relativity rejected the idea of absolute space. In quantum, the reality is just a complex network of events onto which we project sequences of past, present, and future. The whole universe obeys the laws of quantum mechanics and thermodynamics, out of which time emerges. The quantum world is perfect but incomplete. Thank you.